Okay, welcome to Radiation Physics PHZ3302 at Florida A&M University. We are lecturing on the internet because I have been quarantined to my home because I have the flu. So lest we fall too far behind, we're gonna have the lecture anyway. Let me share the screen, the slides, and we'll get started. Waiting for that to come up. Okay. 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 We're going to continue discussing the quantum mechanics of radioactive decay. It's going to be quick and dirty, a little hand wavy. We're not going to do much detail with regard to the deriving anything. We're going to just lift the results of quantum mechanics and discuss them as they apply to radioactive decay. So we're going to discuss the meaning of the decay constant, which we've already discussed actually in previous lecture, and the particular decay mode of beta decay, and talk about the beta emission spectrum. Okay, so the basic description of radioactive decay in the quantum mechanical context essentially is a solution to the Schrodinger equation, first using the stationary potential, the potential that describes the stationary or quasi-stationary nuclear states. You can then obtain the nuclear eigenstates, the stationary state solutions, and then use those wave functions to determine the transition between the states under a perturbing potential, which causes the transition from the parent state to the daughter state. And the transition probability is the decay constant. And the transition probability is given by Fermi's golden rule, that's shown at the bottom of this slide. So the density of final states, the transition probability of the decay constant is proportional to the density of final states. The decay probability or the transition rate is going to depend on the number of possible final states. You would expect a different probability of transition if there were different possibilities for the parent nucleus to decay, essentially. And then the matrix element is exactly what you would expect it to be from elementary quantum mechanics, as just the integral of essentially the dot product of the wave function, of the final state wave function, with the perturbing potential operating on the initial state wave function. All right, so we use the time-independent Schrödinger equation to get the stationary states. And so radioactive decay means that one state, that the probability of finding the system in a particular state as a function of time should be, the probability of finding the state in its original state, the parent state, or the initial state, should decay with time, should be an exponential decay with time. And so you can describe the wave function in time in the following way, as described as the last equation on the bottom of the slide. Okay, so the probability of observing the system in the state with energy EA and interval between E and E plus DE is given by this particular formula. This is also, by the way, the Fourier transform of e to the minus t over 2 tau, where tau is the average, 2 tau A, where tau is the average lifetime of state A. So assuming that the perturbing potential is time independent, the effect of the perturbing potential on states A and B can be described as such. So you starting with state A, then state A, and then the state, basically, again, in quantum mechanics, right, the states all, any particular system exists in a superposition of all the possible states, which means that the nucleus, the isotopic nucleus, or the unstable nucleus, exists in a superposition of the parent state and all the daughter states according to the probability of decay to a particular next state, in the case where you have the possibility for the nucleus to decay along parallel channels with different probabilities. In the case of a single next state, then let's say state from state A to state B, then the state A gets transformed to state B, and so the probability of finding the state in state A drops with time. The probability of finding the system in state B increases in time. All right, so the first specific decay mode we will discuss is beta decay. Beta decay is the most common source of fast electrons, and it's basically results from a neutron being converted to a proton plus an electron plus an antineutrino. So for any given nucleus, the nucleus results in a decay of the starting nucleus of atomic number A and proton number Z, transforms to a daughter nucleus of atomic number A and proton number increased by 1, plus an electron plus an antineutrino. In the quantum field theory context, these decay processes are described more fundamentally in the Feynman view, Feynman diagrams, Radioactive decay is a weak weak or electroweak interaction process. So the decay of the neutron to the proton, electron, and antineutrino would result from the exchange of a virtual boson, a vector boson, the W minus. And in terms of the quarks, the decay process results in the transformation of a down quark in the neutron to an up quark. And so you end up, you started with a UDD, up, down, down, the neutron, and then you ended up with an up, down, up, which is a proton. Okay, so specific, so the next thing we value in beta decay, which is the energy of the decay process. So let's look at the specific example of cobalt-60. So cobalt-60 would transform to a daughter nucleus and a beta particle and an antineutrino. So my question to you is, let me turn on the question and answer. So I'm actually going to, instead of submitting questions, I want you to submit the answer to the question of what would be the element, what would be the isotope, the resulting nucleus, given the rules for beta decay. Okay, so give you just a minute to chew on that. Okay, so anyway, the answer to the question is that nickel is the resulting nucleus. All right, so the energy released by this process is essentially comes from the differences in the masses of the pre and post decay products. So the difference in mass will be manifested as energy, right? Mass energy equivalence in special theory of relativity. So Q, value of the decay, the energy released in the decay is simply the difference between the mass of the cobalt nucleus and the mass of the ejected electron plus the mass of the nickel nucleus. Now, note that the neutrino mass is so small that we don't consider it. So we basically treat the neutrino mass as being 0. And the Q, so the Q is just the energy of the electron plus the energy of the antineutrino, and these really would be the kinetic energies of the beta and the kinetic energy of the neutrino. Okay, so in terms of the decay diagram, we're really on a decay diagram for cobalt-60. We really have only considered the first path, which is the beta emission path. Because a gamma emission, there are two gamma emission paths, which results in the true stable, unexcited cobalt, nickel 60 nucleus, but we're only discussing for the moment the beta portion of the decay path. Okay, so as I stated before, the Q value is the decay energy value of the beta transition, or the energy released in the decay process. The energy and momentum is shared between the electron and the neutrino. So the energy of the electron can only be between either 0 or the Q value. And so the spectrum ends at the spectrum basically ends at the Q value. The particular spectrum that I'm showing here is the energy spectrum of electrons emitted from the beta decay of bismuth 210. But all spectra, all beta electron emissions, kinetic energy spectra, look like this. You know, they start out and then they kind of go up to a maximum and they come down in this same way. So what determines the shape of this spectrum? So, of course, it's quantum mechanics. In the Fermi theory of beta decay, we use the Fermi golden rule for the transition rate. And so, again, the decay is caused by an interaction that is weak. The V prime, the perturbing potential, is it's essentially the weak interaction potential. It's weak compared to the interaction which forms the quasi-stationary states. It's a perturbing potential. You guys who are taking quantum mechanics now, you probably haven't gotten to perturbation theory, but that's essentially what the Fermi theory is rooted in perturbation theory. All right, now the specific form of the perturbing potential was not known to Fermi. We kind of had to guess the nature of the perturbing potential. However, the operator that corresponds to the potential has to have certain properties. And those properties have to be consistent with special relativity. And so since beta decay was something you could observe, then by measuring certain aspects of the emitted products and the daughter nucleus, the transformation properties could be deduced. So the operator had to have certain vector, axial vector, scalar, pseudoscalar, or tensor properties. I just mentioned that for completeness. We're not going to go into the details of what that necessarily means. The thing is that if you're going to describe this process correctly, quantum mechanically, you have to have the right operator. The operator has to have the right characteristics so that when you perform the calculation, you get the right answer. All right, the matrix element, which I'm now calling the matrix element V prime sub Fi. So where previously I was referring to V prime as just the potential, now V prime Fi is the matrix element itself. And so that means V prime Fi is equal to the integral of essentially loosely speaking, the dot product of the final state wave functions with the initial state wave function operated, the the operated initial state wave function, that is the initial state wave function being operated on by the operator that corresponds to the potential, the perturbing potential. Now, in order to determine the shape of the spectrum, because the spectrum shape is really a measure of the statistics of the probability of measuring emitted electrons with a given kinetic energy, you need the density of states to determine the shape of the spectrum. So what's the meaning of the density of states? So if we consider the momentum of the the momentum of the situation, excuse me. If we consider the momentum of the situation, the original nucleus decays at some point, and of course the momentum of the final products have to be equal to the original momentum. Now in the diagram, I've actually shown here an initial in a situation which is not in the frame of the original nucleus, but obviously the easiest choice for doing the analysis of momentum states is really to do it in the rest frame of the original nucleus, so that the original momentum is 0. But in any case, momentum has to be conserved, regardless of what frame you're viewing a process in. So if we consider the momentum state space, if we consider a sphere of momentum values, a sphere in momentum space which corresponds to a single momentum magnitude, right? The momentum's a vector, right? So it can point in any particular direction in momentum space, right? That means that for any given magnitude of momentum, you can have any combination of X, Y, and Z momentum components, okay? So the volume of the shell in momentum space in which you might find electrons and neutrinos and the antineutrino. And I forgot to put the bar over the neutrino symbol in my diagram. The antineutrino measured between some momentum and some momentum plus delta momentum would be given as described in order to make the units work out. One has to divide by the Planck's constant cubed, because that is the unit volume of 6-dimensional phase space. So the 6 dimensions of phase space are the spatial dimensions and the momentum dimensions altogether. So X, Y, and Z, and Px, Py, and Pz form the 6-dimensional phase space. So the number of electrons in the shell of width dp would be 4 pi p squared dp v over h cubed, and the number of neutrinos for beta decay antineutrinos d would be dn neutrino. The number of neutrinos in that differential shell would be 4 pi q squared dq v over h cubed, where I'm just labeling the momentum of the neutrino as Q, and the momentum of the electron is P. Now, the momentum of the daughter nucleus is considered to be so small. Most of the momentum is carried by the neutrino and the electron. Okay, so the number of electrons and neutrinos found between the momenta P and P plus dP and Q plus PQ is given as shown. So that's the density of states. And then in order to do that integral, you need the wave functions for the emitted electrons and neutrinos. So the emitted electron and neutrinos are the wave functions. They're now free particles. So the free particle wave function is the correct description of their states. And so the electron has a free particle wave function corresponding to electron, and the neutrino, antineutrino, I keep forgetting to put the bar over the neutrino symbol. The neutrino wave function has a wave function that is described by a wave function, which is a free particle. Now, it turns out that you can make an approximation with regard to what the wave function looks like mathematically, because for most beta decay, the energy of the beta particles is usually around 1 MeV. So the momentum is about 1.4 MeV over C, and 2 pi of the momentum over the de Broglie wavelength is about 7 thousandths of a femtometer. So that means that you can argue that the momentum, the dot product of the momentum and the position vector is going to be very small, much less than 1. So the exponential basically looks like 1. It's e to the something very small, e to the almost 0. So the wave functions basically just look like 1 over the square root of the volume. Okay, putting that all together, I'm going to leapfrog forward. Putting that all together in the Fermi-Golden rule construction, you can construct a differential for the decay constant, and you can okay. And so then the number of electrons at momentum P is basically just given by this term C times P squared Q squared dP. The C basically just contains all the other terms. And then the Q basically, the Q, the momentum of the neutrinos has to be the Q value of the decay minus the kinetic energy of the electron divided by C, which you can then rewrite in terms of the relativistic energy, the relativistic, what the kinetic energy is in terms of, as described by special relativity. And so if you do that, you basically get what you have at the end here. and that's basically the description of the, that's essentially the description of the of the beta decay spectrum. Okay, I'm gonna stop here, and I'm going to take some questions before we go on to the next part of the lecture. So please submit questions. I'll give 2 minutes for submitting questions. Okay, 2 minutes for submitting questions. No questions? Okay. All right, so if there are no questions, we'll just move on. I need to open up another presentation, so bear with me just a moment. Okay, I need to close this. Okay. One moment, please. Please stand by. Okay. So the next thing we're going to do is internal conversion. And okay. Okay, I need to share something else. All right, so we're now going to discuss internal conversion. Well, we're going to discuss actually two atomic electron emission processes, internal conversion and Auger emission. So in internal conversion, basically what happens is that in quantum mechanics, there's a probability that the wave function of an electron in a low energy shell, I believe the K shell, and that a K shell electron can overlap the wave function of the nucleus. That essentially means that there's a probability that the electron finds itself in the nucleus, in the atomic nucleus. So when that happens, the electron can actually couple to an excited state of the nucleus, and essentially take the energy of the nuclear transition directly without there being a photon involved in the process, a real photon, okay? So whereas if this were described in the quantum field theory context, there would be the exchange of a virtual photon. But in the case of a real photoelectric process or electromagnetic process, there's no real photon produced in the internal conversion process. Okay. All right. So the way this is described from a I guess a quasi semi-classical view is the multipole fields, the multipole electromagnetic fields of the excited nucleus interact with an atomic electron and then cause the electron to be emitted. And so the emission energy of the electron is equal to the energy of the excited nucleus minus the binding energy of the electron. So in other words, whatever the binding energy of the electron, of course, is however much energy it would take to eject the electron from ionization from the atom. Okay, the second electron emission process we're going to discuss is just the Auger emission process. So in the Auger emission process, you have the following possibility. So you could have for instance, an atom, and then you could have an electron collision or a photon, an electron or a photon scattering off of an electron in a lower energy shell, and that electron gets ejected. That leaves an empty state in that shell, and then a electron in a higher energy shell drops to occupy that empty state. But instead of a photon being emitted, an electron, the energy the released energy can manifest itself instead of as a photon, but as an electron, which is ejected from another energy state. And so that's kind of weird, but it happens. And the description of the energy of the electron is the same for Auger's internal conversion. However, the Auger emission are favored in low Z elements. So now I want to ask the question, why is the Auger emission favored in low proton in elements where the nucleus has fewer protons than more protons, which essentially be same as low atomic number elements. So if you can submit your answer as a question in the question and answer tool, okay, so I'll just give a second for folks to submit their answer. Okay, so the reason why it's favored in low Z elements is because the lower Z elements have a smaller electron binding energies. So it's more likely you're going to get electrons ejected in that case. Okay. Okay, so on to the next thing we're going to discuss is alpha decay. And we'll be discussing alpha decay for a little bit. All right, so let me open that and share that presentation. Okay. Oh, okay. Okay. All right, just give me a moment. I need to open up that particular presentation file. One moment, please. Okay, just need to. Okay. 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 So now we're going to discuss alpha decay. So the alpha decay is basically the release of a helium nucleus. And so whatever the starting nucleus is, the daughter nucleus will have an atomic number reduced by 4 and a proton number reduced by 2. A helium nucleus will be ejected. So in the alpha decay process, the alpha particles are emitted in monoenergetic groups. The Q value, the energy of the decay is shared between the recoil nucleus and the alpha particle. And I shouldn't say equal, it's proportional to the atomic number minus 4 divided by the atomic number of the decaying nucleus. And alpha particles are easily absorbed or blocked. I think we discussed this in a previous lecture as well. So, question, why does alpha decay occur? So in the classical answer to this question would be because of Coulomb repulsion. The force on the Coulomb, the force on a proton in a nucleus basically goes as the square of the number of protons divided by the distance, the average distance between the one proton and all the other protons together, right? So the Coulomb force increases the square of the number of protons. However, the nuclear binding increases only with the atomic number. So the Coulomb force increases faster than the nuclear binding. So the classical analysis of this is to consider a nucleus, consider a proton on the edge of the nucleus. the force that proton feels is basically just ZE squared divided by the radius of the nucleus squared. So Z, the charge of the nucleus, can be described by the volume of the nucleus times the charge distribution, which I call lambda sub Z. So if you stick that in for the force in the Coulomb electrostatic force equation above, then the force is described as lambda ZE 4/3 pi r. So you see basically that the force is linear with the side. It goes up with the radius. Okay, so there are a couple theories of alpha decay. We will discuss at least two of the alpha decay theories. So all decays must obey the conservation of energy and the conservation of momentum, and of course the conservation of angular momentum, and also actually the conservation of some other quantum mechanical properties, which we will mention later, but we won't discuss them in detail at the moment. So if you take a general equation for alpha decay, basically the energy of the pre-decay situation has to be equal to the energy of the post-decay situation. So what starts out as a nucleus before decay, the energy is basically just given by the mass of that nucleus times c squared. We are assuming that it's at rest, or we're in its rest frame. And so the energy basically in the post-decay is basically the rest energies of the post-decay products plus the kinetic energies of the post-decay products. So the Q value is the mass. The Q values can be described as the kinetic energies of the post-decay products, or the mass difference between the pre and post-decay products, the rest mass difference between the pre and post-decay products. And of course, the momentum has to be conserved. So we're gonna most of our analysis of alpha decay is going to be in the non-relativistic case. By the way, this lecture is going to go past 9:55, so I apologize for that. But in this case, it's being recorded, so you can look at it again on YouTube. Just use the links given in the Blackboard, so you can review this lecture again. In the non-relativistic case, the Q value is much less than the rest masses of the decay products. So what does that mean? Well, that means that when you write the kinetic energy in terms of special relativity, you basically get a term under the radical, which can be approximated because the p squared c squared is going to be much less than the m naught squared c to the fourth. So you can actually approximate that using a binomial approximation. And when you invoke the binomial approximation, you can basically approximate what's under the radical as shown. on the last line of the slide. And then it turns out that the kinetic energy is just p squared over 2m naught in that case, which is exactly what you would expect from Newtonian physics, right? Kinetic energy is p squared over 2m. So now if you apply that, if you apply the non-relativistic analysis to our specific situation of alpha decay, we have the kinetic energy of the post-decay product would just be the p squared over 2m, the momentum squared of the post-decay nucleus over the 2 times the mass of the post-decay nucleus. And you can go further to show that the kinetic energy of the alpha particle is given by the Q value of the decay times 1 minus 4 over the atomic number of the nucleus. The working assumption here is that the mass of the alpha particle is much less than the mass of the nucleus. Okay, so that's the end of this lecture. Next time we'll discuss the alpha theory of Gamal, Gurney, and Condon, which is a more further quantum mechanical. Okay, I will see you next time.